Okay, welcome everybody to today's seminar. We have Gabriel Pallier who will talk about sublinear bilipschitz equivalence and symmetric spaces. Please go ahead.
Hello everyone, many thanks for having me here. So I will talk about joint work with Ido Grayevsky. He's in Jerusalem currently and he will be moving to Bristol soon. So to introduce the setting, I will need a function throughout this talk that I will call V, and which goes from 0 plus infinity to 1 plus infinity. I will ask it to be non-decreasing, and especially to be that such that V of R divided by R tends to 0 as R tends to plus infinity. Okay, I want to emphasize the fact that R is going to plus infinity. This is a manifestation of the fact that we are dealing with large-scale geometry in this talk today, and so what matters really is large scale. And another feature which is more of a technical one, which is I will assume it to be so that everything I say is correct. I need to do this assumption. So first, a function. Now I need two spaces, x and y. So they are pointed metric spaces. And I will denote the distance to the base point in this way. In both spaces. So now I give the definition, which is a notion introduced by Cornulier in 2017. So f going from x to y is O of v by Lipschitz equivalent if there exists some lambda larger or equal 1 and there exists some c larger or equal than 0, such that, so there are two conditions. The first one is that the distance between f of x1 and f of x2 should be controlled, so on both directions. There is an upper control by lambda times the distance between x1 and x2 plus v cv of x1 and x2 on the one hand, and on the other hand I want it also to be larger than 1 over lambda dx1 x2 minus cv of x1 plus x2. And the second condition, so this is something I ask for every x1, x2 in x, and the second one is something I ask for every y in the target space. So distance between y and f of x should be no larger than c times v of y. So for all y in y. So this is the definition. So I make a few remarks now. A few remarks. So the first one is the following. So if you take v equal to 1, O1 by Lipschitz equivalence is more known actually as quasi-isometry. The second remark I want to make is that OV by Lipschitz equivalence is an equivalence relation. So we take this as an equivalence relation on metric spaces, and these maps can be checked that they compose well. And what I will talk a sublinear by Lipschitz equivalence is some OV by Lipschitz equivalence for some V. So sublinear by Lipschitz equivalence is defined as OV by Lipschitz equivalence for some V. So for 2, you could take this as an exercise. If you've done it for quasi-isometries already, it's not too hard. Otherwise, maybe you start with quasi-isometries, and it's exactly the same kind of proof. It's just you need to work a little more, but it's the same reasoning. So okay, so that's my second remark. And the third remark I want to make is that I need a base point for the definition, but they don't matter that much actually. So I define this between point and metric spaces, but what happens if I change base points? So if you move them by a distance delta, say, then if you look at the old distance, it's controlled by the new, the distance to the old is smaller than the new plus delta by the triangle inequality. And if you check now that if you look at V of R plus delta or V of R plus 2 delta, it's still, so now V of R plus delta by subadditivity is smaller than V plus R plus V delta. This is a constant, and this is still O of V of R. And so what may happen if you change base points is that the constant C here might change. So changing base point may change C. But not lambda, and no V. This is maybe slightly troubling because this doesn't happen for quasi-isometries, but we don't care about this constant C too much actually. V matters much more. Are there questions so far?
So to keep sort of building intuition for this, if V were actually linear, then this would be vacuous, right?
Yeah, we don't really look at it for linear because otherwise this equivalence relation would be very loose. I think.
But it completely vacuous, right? It would just be all metric spaces.
Yeah, bounded or unbounded, maybe, or, but it would not be very fine. So,
yeah, so it's like interpolating between quasi-isometry and nothing.
Yes, exactly. Exactly. So it's important that it's strictly sublinear, otherwise we don't get a very fine relation. So that's the next question. The question actually is how flexible is this? It's this notion. So I want to give a few examples to build intuition. So I will give some examples which are somewhat artificial, but I want also to show you that this happens in nature. But first I show you the artificial examples. So these are the following. So I will take three metric space that are three Riemannian planes. That are embedded in Euclidean space. So the first one is a half cylinder that I close with a cap. So that it's a plane. The other one, the second one is elliptic paraboloid, so it looks a bit like that. So that Z is x squared plus y squared. And the third one is hyperbolic paraboloid, so that Z is square root of x squared plus y squared plus 1. So I will call them x, y, and z. And okay, but you can put base points OX, OY, and OZ. And the point is now is to figure out which of them are sublinear bilipschitz equivalents. And so I will state the solution and say how we do that. So facts, three facts. If you look at the first thing I want to point out is that x and y are square root by its equivalent. The second fact is that x or y, x and y are not SBE, sublinear bilipschitz equivalent. To Z. And the third fact is that x and y are not quasi-isometric. And there are many ways to see this, but so let's think a bit about this. So for the first fact, you can use that in fact, so proof for A. You have several ways to do it, but you can notice that you can send rays, geodesic rays into X and Y, for instance. Geodesic rays. So there are geodesic rays into X and Y. And they are globally geodesic. And so what happens is that they obviously have the condition 1, and it's not too hard to check that they also have condition 2. So I check it for y, so if you take any y in y here, say it's at a distance about r from the origin, then the distance to the geodesic here is about square root of r, right? Times some constant. So you can do that. You can also use the height function if you prefer height functions. So if you use height function, then 2 is going to be obvious, but 1 is the one to check, but it's not very hard either. So the same reasoning tells you that actually x is quasi-isometric to the half-line. And so that's for A. So for B now, B needs something slightly more sophisticated because we need to rule out the existence of a sublinear bilipschitz equivalence. And so for that we use, there are several ways actually, you can have several ideas to do that, but I want to point out the asymptotic cone. And pointed asymptotic cones actually. So the informal way of seeing that is doing look from infinity or from infinitely far away. So you know these are surfaces. They have non-negative bilipschitz curvature for the three of them, and so this allows to take some limits of rescalings. So if you take define, for instance, so for all k larger than 0, define first x and k to be the ball of radius nk in x, and then if you take the sequence x and k with 1 x and k with 1 over n dx, this Hausdorff converges to some ball of radius r in some space that is called the asymptotic cone. Of radius k, and x infinity is the asymptotic cone of x. Right? And here for x and y and z, it's not too hard to figure out what the asymptotic cones are going to be. So they are going to be, so you can figure it out while I erase the board actually. so the solution is as follows. So for x, so x infinity looks like that. It's a half line. Y infinity also looks like that. The point being that if you move at height, the point being that actually square root of kn divided by n, this tends to 0 as n tends to plus infinity. So the width is, you don't see it in the limit. But z infinity now is a cone, is a true cone, and it has, so it has covering dimension 2. And the thing is that if there was SVE from f from x to z, then it will induce a bilipschitz homeomorphism from x infinity to z infinity. This cannot be because these have different dimensions. And so why is that? So I just erased the definition, but v of x1, x2 is sublinear somehow. And so when you divide v x1 plus x2 by the distance to the origin, this tends to 0, and you don't see v in the limit. So what you see in the limit is just a bilipschitz homeomorphism. So this cannot be. Are there questions? Okay, right. So now I want to do C. So C, there are many methods again, but I want to emphasize asymptotic cones again, because asymptotic cones and quasi-isometries are actually linked in a certain way. You can still use asymptotic cones to distinguish x and y up to quasi-isometry, but you need to move the base points. So how do you use that is you take an point at height n squared on y, right? And now I'm going to look at the balls of radius kn around an. And now you take, so y and k an with balls in y around an of radius kn. And then what I say is that this with 1 over n resistance from y, Hausdorff converges now to some space that you might be figuring out that is actually a cylinder. Right? The point being actually that square root of n squared minus nk is about square root of n squared. So when we normalize by n, you find 1. So this at width 1 actually. And you don't see a difference of width upstairs and downstairs, because n is small compared with n squared basically. Well, okay, but now if there was some quasi-isometry from y to x, you would do the same construct, some quasi-isometry f, say, you would do x, you would do the same construction with x, so x of f of an and k with 1 over n dx. Now, this Hausdorff converges to a line, actually, because the point f of an is moving up, and you don't see the width anymore. So this is dimension 1 and this dimension 2, so there cannot be a quasi-isometry. So there are other ways to solve this little problem, but I want to emphasize this. Yes?
Why is it enough to take the same points on? Can you just explain how?
Well, it's not enough to use the same point. If I use the same base point, I get the same asymptotic cones. Is this
But why the fact that there are some sequences of points which doesn't give you quasi-isometry, which doesn't give you a bilipschitz homeomorphism, implies that there is no quasi-isometry?
Yeah, the fundamental point is that quasi-isometries, they go through asymptotic cones through every base point, even moving base points. You can take asymptotic cones with moving base point and the quasi-isometry will go through. And this is actually a definition of quasi-isometry. which is a bit involved, but this is one way to define quasi-isometries is to say they are the largest class of maps which goes through asymptotic cones through every wave point and give bilipschitz homeomorphism in the limit. And bilipschitz comes for free if you assume the space larger than this.
Okay.
Sorry, did I answer the question? Or?
I mean,
maybe
I don't know this proof, but yes.
Okay, maybe I write just what I wrote. Just like what I wrote here is that so if there was quasi-isometry, f from y to x, it would induce a bilipschitz homeomorphism. Between these two spaces, from the cylinder to the line, it's not possible. Again, because okay, it's not bilipschitz, it's bilipschitz at two constants, but the constants you divide, you rescale them, it goes to 0. And
can I ask a question?
Yes.
So here you're looking at height n squared,
yes.
both in y and in x.
Yes.
What if I looked at n square in one, but n cube in the second space, or some other height? Like
In the second space, it's just looking at f of whatever the height n squared thing is.
Okay.
Exactly.
Okay.
And if I look at n squared, it's good because it gives me a cylinder, so I still have a good space. And here f of an will be also about at 8n squared because it's bilipschitz on the large scale, so it's about n squared. Okay. So these are somehow a bit artificial, but now there are examples of homogeneous manifolds which are linear bilipschitz equivalent quasi-isometric. So I give them to you. Actually, the first is a hyperbolic free space. So here it is. If you take, so I'm going to take x, it's going to be a hyperbolic free space, but I want to write the metric in certain coordinates. So it's R2 times the positive real number, and with the Riemannian metric, which is dx squared plus dy squared plus dz squared divided by z squared. So this is isometric to H3. And the second one is y, which is also a homogeneous space, a space which will have a transitive group of isometries, and is in the same coordinates. So the metric is slightly more complicated. It's 1 plus log squared d dx squared minus 2 plus d dx dy plus dy squared plus dz squared divided by z squared. That's all. And so it's a homogeneous space. So y is a homogeneous space. And so there is this theorem by Cornulier that's actually from 2008. I said to you introduced the definition in 2017. So in this paper, it's not defined, but this is the paper which gives the fact that actually x and y they are U of log bilipschitz equivalent. And you can even take lambda equal to 1 actually for these two. But you can confront this with the theorem of C, which says that they are not QI. They are not quasi-isometric. So this is indeed a different notions even for homogeneous Riemannian spaces.
So what is the isometry group of Y?
It's a semi-direct product of R2 and R, which acts simply transitively. So it's a three-dimensional Lie group, and you can actually prove that. So this is negatively curved, so it's pinched somehow. But you can take some other metrics on these same Lie groups, which are pinched arbitrarily close to -1. Somehow it looks a bit like that, but it's not that.
And even with the other metric, the same conclusion holds.
Yes, the fact is, yes, when we have groups, you don't worry too much about the metric you put, that's the Schwarz-Miller lemma. If you put two left invariant Riemannian metrics on the same groups, they are quasi-isometric, they are even bilipschitz. Okay, are there other questions?
So this other group, it doesn't have a lattice.
Yeah, right. So this, they are lattices, so they are discrete groups quasi-isometric to this one. But this, no, it doesn't. The Lie group is not unimodular, so it has no lattices. But even better than that, there are no finitely generated group quasi-isometric to this one. This also follows from CS work. Yeah, so somehow they occur in nature. But what you should understand by nature is Lie groups and not so much finitely generated ones. So now I state the main theorem. So there are still a few words that I didn't explain in the theorem, but I will explain to them just after that. So yes, and I want them to have no compact factors, so this is important. Otherwise, the statement is a bit more cumbersome, so at least we try to write, so they have no compact factors. If they are sublinear bilipschitz equivalent, then they are pluri-homothetic. Right, and I should say that for this is so for quasi-isometries, this is due to Kleiner and Leib. So for quasi-isometries, this is Kleiner-Leib 94. Right. So yes.
What does for quasi-isometries mean?
If you replace, good question, thanks. If you replace sublinear bilipschitz equivalence here by quasi-isometry, so for V equal 1. Okay, that's for V equal 1.
And so what is pluri-homothetic?
Yeah, this I will explain.
It got a factor in isometric in respect of times, so.
Yeah, so there is something called the de Rham decomposition. I will recall and I will explain what it means. So some words, so some vocabulary. Um, So symmetric space means so it's connected, and for all x in x you have a geodesic symmetry. Such that dx sigma x is minus 1. So this is just the definition, it doesn't tell much to you, but as it happens, they have so-called Durand decomposition. So this word does not appear in the statement, but I needed to define pluri-homothetic. So if you take a symmetric space, it's going to decompose, so X symmetric space. Then there exists RPQ, such that X is actually a Euclidean space. This we call the Euclidean factor times connected factor with compact factor. Sorry, that I want to not care about. And then after that, some other factors. So x1. So there is this decomposition where xc is compact. So you can think, for instance, of SU2 mod SO2, which is S3. But I typically don't want them in the theorem. Xi they are rank 1, non-compact type. So you can think of H3, for instance, which is SO031 mod SO3, and also XJ2 are higher rank. Non-compact type, irreducible. Irreducible. And here you can think of SL3R modeled out by SO3. And so this sometimes people call it S3. And rank, I didn't define rank. So actually Nathaniel said it last week. Rank is the largest dimension of totally geodesic Euclidean subspace. And now multi-homothetic means pluri-homothetic means we are allowed to do a homothecy in every factor of the Durand decomposition. We are allowed to do, so it's a homothecy in every factor of the Durand decomposition. So you're allowed to rescale them. So I should say that except the Euclidean ones, actually, they don't have auto self homothesis. So we could also have scaled them well so that it becomes isometric on the non-Euclidean part and homothesis on the Euclidean part. But this is okay. So the thing is, the only thing you can do is rescale one of the you can rescale every factor in the theorem decomposition. For instance, you take h3 times h3, you rescale by a constant in one factor and another. That's the only thing that can happen. So they are basically the same, actually. They are sublinear bilipschitz equivalent. So this is in contrast with the statement I gave for homogeneous spaces, where you could see that some homogeneous spaces were sublinear bilipschitz equivalent, but not quasi-isometric. Here it turns out that the result is the same as Kleiner-Lebs, so they are sublinear bilipschitz equivalents if and only if they are quasi-isometric. Are there questions? Yes?
So can you also show that so if you have such a sublinear equivalence, then
Yes.
it's in a sublinear distance to isometry.
Yeah, so my co-author Grayevsky proved this for higher rank irreducible, or if you avoid rank 1 factors. If you allow rank 1 factor, then it's already not true for quasi-isometries, and we don't know the answer in general for sublinear bilipschitz equivalence.
Just a question.
Yes.
Okay. So in this case, with the homology, you mean read the Euclidean homology, but
Yes.
if you are, sorry, for instance, in the hyperbolic space or in the alternative, what do you mean with the homology there?
Yes, there are no homotheties, right? But the thing is, for me, the hyperbolic space with constant curvature -1 is a symmetric space, but also the one with constant curvature -4, right? I didn't.
You are fixing the. Okay, got it.
I could also have normalized it.
Okay, got it.
Okay. So, okay. So I will tell a few words about the tools we used for this. So some of the tools are in common with Kleiner-Lebs, especially so for certain symmetric spaces, and some are slightly different. So I will explain that. And I let them answer them for now. So tools, so how it works. So the first step is to treat the case where rank of x is rank of y is 1. Second step is treat irreducible higher rank case or rank avoiding compact factors. Treat higher rank irreducible. Right, actually I will skip to the Pi's case, deal with products. Okay, and after that there are the Euclidean ones, but so that's the three steps of the strategy. And so a few words on one. So one. So what are the rank 1 symmetric spaces? Actually, there is a list. So rank 1 symmetric spaces. So rank 1x. So there is a list which is the following: the real hyperbolic spaces, the complex hyperbolic spaces, the quaternionic hyperbolic spaces, And the last one, which is an isolated one, and which only exists in one specimen, which is the Cayley hyperbolic plane, which is this one. And so what I want to do is, so now there are rank ones, so they are Gromov hyperbolic. Actually, the constant, the curvature is bounded above by a negative number, and this allows to do some analysis on the boundary. So there are conformal charts for the boundary. So here it's the first case, it's Euclidean. So it's just e to the n-1. The second one is Heisenberg group. Here, after that, it's quaternionic Heisenberg group. And octonionic. And what they have in common is that these all are non-smooth for the last three sub-Riemannian spaces. So they are sub-Riemannian. So all of these are Carnot groups, so-called Carnot groups, with sub-Riemannian metrics. And now I put the theorem in 2020, which says what happens when there is an a sublinear bilipschitz equivalence between such spaces. It's valid actually for Gromov hyperbolic spaces. And we assume that there is a sublinear bilipschitz equivalence, so O of D between the two. And now it extends to the boundary. And it extends to the boundary in a way. There exists the so-called O of V quasi-symmetric homeomorphism. And the case where V equals 1 it goes back to Gromov actually, even longer ago if you consider symmetric spaces, and it's the well-known class of quasi-conformal or quasi-symmetric maps when V equals 1. So homeomorphism. So I will not give the full definition of OV quasi-symmetric because it's a bit involved and you need to state it at least for 3 points. There is a version for 3 points. So it's a version for 3 points, and still you also have the function V, so it makes a lot to write. So I want to just make a drawing of what it makes. And especially contrarily to usual quasi-symmetric homeomorphism, it distorts the moduli. So O of V quasi-symmetric. So it may distort moduli. So if I draw, so now I'm doing a drawing here is the infinity of x and here is the infinity of y. So it may distort moduli. So here are 3 balls, 3 concentric balls with geometric progression as radii. So it may distort the moduli, but not too much at given scale. So I want to say that here, if I took some psi and some r, and here some log of r, the modulus of this annulus is log of r mod r. The modulus here is log of r divided by r, and the modulus in the image typically is not going to be larger than 2 lambda m, so lambda is the constant of the SBE, plus, and here is the thing, O of, yeah, I don't have room, so let me write it upstairs. So it's m prime, here is no larger than 2 lambda m plus O of V of minus log R. So at given scale, it's bounded by a sublinear function and it doesn't go too fast to infinity as the scale goes to 0. So it's not as good as quasi-conformal. But the thing is that now what I could prove is that it still preserves the conformal dimension of this. Yeah, so so O of V quasi-symmetric homogeneous between open sets of Carnot groups. They preserve the conformal dimension. Right, and now the conformal dimension, which is, so this is the conformal dimension can be defined as the infimal Hausdorff dimension among all the quasi-symmetric metrics, quasi-symmetrically related metrics to the metric space. So this is somehow, this is the Hausdorff dimension, and this is really the Hausdorff dimension of the, if you never met conformal dimension, you can take this as Hausdorff dimension because the sub-Riemannian metric is actually doing the job in this case. These are very nice Loebner spaces. And the thing is that now the conformal dimension, I should have plotted it in the table. So CD of the boundary. Here it's just n minus 1. But now here it's so instead this is 2n dimensional, so it's 2n. Here it's 4n plus 2, and here it's 23. The thing is that the conformal dimension, together with the topological dimension of the boundaries, they allow to recover x. And so this is done. So I would like to point out that actually, so for quasi-isometries between rank-wide symmetric spaces, this is due to Mostow, the theorem above. But Mostow is, so it starts the same, it extends to the boundaries, there it's quasi-conformal. After that, there are very good properties of quasi-conformal homomorphism that they are absolutely continuous on lines. And this fails for for OV quasi-symmetric. So Mosto proves the theorem above, the same theorem. It's a remark in his books actually. For V equal 1, but he uses that quasi-conformal homeomorphism as the ACL. And this is not which phase for OV quasi-symmetric, even between open subsets of R2. I constructed examples of those creatures that don't have the ACL property, and so there is a derivative, but it's almost everywhere 0. Or it's almost everywhere degenerate, sorry. And so it's not like quasi-conformal. This fell for OV quasi-symmetric. Homeos. Are there questions so far? Okay, so now I can go to part 2. So part 2 is about my co-author Grayevsky. Actually, it's not my work. It's so it's the theorem of my co-author, 2023, and it answers Alexander's question. So he stated it for a single one. So I stated as he proved it. So let X be a symmetric space with no compact factor, no Euclidean nor compact. And let f x to x be a O of V. No, for the bilipschitz equivalence. Then f is sublinearly closed to another isometry. I should say that this is only a little part of Grayevsky's theorem. He proves it for compact core of non-uniform lattices as well. A similar statement. And so.
You also assume no rank 1?
Oh, yes, there is. Thanks. No rank 1 also. No rank 1 factor. With no rank 1 factor. Thanks. And O of V close means F and G are O of V closed if f of x, distance of f of x, and g of x is in O of V of x plus. So for V equal 1, this is again due to Kleiner and Leib. And it's also given by Eskin-Farb. There are several differences between Kleiner, Leib and Eskin-Farb. And Kleiner, Leib, they use asymptotic cones a lot. And the very useful fact is that the asymptotic cones of these spaces, yes, they are Euclidean buildings, stick Euclidean buildings. And so Grayevsky's techniques are in spirit closer to Kleiner-Leib's and especially Drutu's techniques, and slightly different from Eskin-Farb's. But I should nevertheless say that for V1, this is Kleiner-Leib. 94 or S2 90, I don't 96, I guess, something like that. So this is part of a more general theorem because Grayevsky proves a sublinear rigidity theorem, and for this he has to prove more, and but still using a lot asymptotic cones. As we have seen, sublinear bilipschitz equivalents, they like asymptotic cones, and so this is one of the points of doing this. And so, okay, this is a statement for a single symmetric space X, but we want it for two spaces. But now what can we do is that we can, so from X, as above, as in Grayevsky's theorem, consider the group G of the F, X to X that are O of V SBEs modeled out by the Hausdorff closeness relation. And at first it looks like a huge group, but in fact it's isometric to, it's isomorphic to isomorphic actually. So you recover G such that X is G mod K in this way by Grayevsky's theorem. So, and this is a SBE sublinear bilipschitz equivalence invariant. So you recover G, you recover X, and you're done. I don't know if there is a relative version. For planar and Leb, there is a relative version. Okay, so this is done for step 2, and now I just have 3 minutes maybe, or yes, or maybe 2 minutes. So this is done for step 2, and for step 5, this is what we actually did with Grayevsky last year, is to generalize this theorem by Kapovich, Kleiner, Leb. So there is an earlier version of this in Kleiner Leb, which is sufficient for symmetric spaces, but we did the more general version of Kapovich Kleiner Leb for about quasi-isometries between product spaces. From quasi-isometries to ORV bilipschitz equivalence. So it basically says that if you start from you start from a ORV bilipschitz equivalence between these symmetric spaces, you look at the Durham decomposition. There are the Euclidean factor and all the other ones. The O of V bilipschitz equivalence is going to induce O of V bilipschitz equivalence downstairs between all the non-compact factors, irreducible non-compact factors. And then you apply step 1 or step 2, and you get the result for the non-compact part. This is also a theorem. What especially favorable for us is that the proof here is really using asymptotic cones a lot. So we could manage to do it for O of V bilipschitz equivalence without too much pain. And I should stop here. Thank you.